AmeriFlux management project, which supports the AmeriFlux community and sites to ensure the quality and availability of the continuous long-term carbon, water, and energy flux data. His research interests are understanding and building the mechanistic linkages between ecosystem characteristics, functions, and processes. And he's the developer of this AmeriFlux R package, which facilitates the query, download, and use of AmeriFlux data. So, Xiangming, why don't you go ahead and share that recording with us?
Okay, so first, at hosting, hosting asked me to share this two links about his material, and now I'm going to share his video, his recording presentation. Share. Okay, so let's start.
Hello, everyone. Welcome to today's webinar. I'm Hao-Sen Chu from Lawrence Berkeley Lab. I'll be happy to talk to you about AmeriFlux R, an R package for interfacing with the AmeriFlux data today. Sorry, I cannot be here today, but feel free to reach out to me if you have any question after this webinar. I'd like to acknowledge my cooperator, Koen Hofken, for helping the develop of this package, and also the support from AmeriFlux management project make this package possible. So AmeriFlux is a very diverse, large network of the eddy coherent site shown by this map, or the color coded by different means a different IGBP type, and the circle means the data record. So you can see there's many different type of ecosystem, and also highlighted by this photo here. But also the very long data record. Today there are more than 500 sites with more than 400 sites available, data available for download, and also almost reaching to 3,000 site year of data. It's been growing on average 300 site year every year. And this brings up why we are developing this R package. It's allow the user to interface with AmeriFlux web service for querying, for downloading, and for the use of AmeriFlux data and metadata. Okay. So this is just a structured workflow of the typical AmeriFlux using a AmeriFlux package, starting from site selection, obtaining additional information, and once you decided the site you have interest, you want to for your research, and you can download the data, import the data, and clean everything on your own for the further step. And the package is released through our CRAN, so you can install the package like a typical R package here. Some highlight of the package allow you to just query the site, the most updated site of the AmeriFlux through just one function like this one. And also to download, for example, the metadata just through one function like this. You have to specify your user ID email through the AmeriFlux account. And once you download, you can read in the file. Similarly, for the so-called base file, the FluxMet data file, again, this can be downloaded through just one function and read the file in R. I'm going to show a tutorial today, and the R Markdown file will be available on the GitHub. If you have time and interest, I encourage you to go to the AmeriFlux page website. There's some more detailed tutorial about how to use this package for site selection and data import. For today's demonstration, I want to show you, for example, I want to test a new model I'm developing. I have interest about cropland and grassland site. Latent heat is my target variable. I want to also make sure the site have the outgoing long-wave radiation, air temperature, humidity, also some information about canopy height. Because I'm using the remote sensing certain products, so I want to make sure that the data is available between this period. And I'm going to follow roughly something like this workflow, just keep in mind, okay? So this is the R Markdown. You can download this file through the GitHub. Loaded the library first, of course. First thing we did is use this function to query to get a full list of the site of the Merflux. Okay, this is now the site here. As I showed you earlier, this have a site ID, site name, and all some of the basic information like IGBP, the tower started year, ending year, etc. And sometimes this might be enough for you to do subset of the site. We can start with this site list. Okay, let's select the site with a cropland grassland and make sure there's some data available within this period, and they need to be CC by 4 on data use policy. Okay, now we subset the site to 74 site now. Okay, so we're not dealing with 500 site. Next thing we did is, okay, let's get an idea about the metadata availability. Okay, especially we want to know if the canopy height is available for some of the site. We can use this list metadata function to get the data coverage of the metadata. Then we want to make sure there's some canopy height available. Let's return everything to this new list here. Okay. Now the crop list 2 have only 11 sites, and this 11 sites based on the criteria we just talk about everything there, and make sure there are some canopy available. There are more than 100 entries for some of the site, and some of the site only have few available. It's okay. Next thing we want to know is about the data availability. Okay, we can use this data function, and we can use a site set parameter to make sure we just focus on this the sites we select already. And everything now return to this data availability data frame. This show you inside this data frame, there's some information about the site ID, the variable name. You can see here with a qualifier. I tell you the position of each of the variable, and also just base name. So this is just a variable name here without qualifier, and the data coverage for each of the year. You can see the data started with 2003 all the way to 21. Okay. Then we can use this information to subsetting the site and also the variable we have interest. We want to focus on this couple of variable we already mentioned earlier. We want to make sure they are not get filled. We especially want to know about the data coverage over these 5 years. So we create another variable, average of the data coverage. We want to make sure they are not 0. Now we have a new crop list 3. Again here, very similar, site ID, variable name, best name, data coverage for each of the year. And you can use this information to get closer look of the data you want to play with. Another very handy function would be just plot this data availability coverage just through an interactive plot. Now we are, let's take a look of the latent heat here. And this is a latent heat for the subsetting site we just did, right? You can take a look for each of the year, what is the data coverage of the latent heat? Pretty good. These 2 sites, okay, they are maybe deactive after 2017 or 18. So there are very few data coverage, very low data coverage in this year. And for this demonstration, we probably want to take this one out because we want a little bit more data coverage through the entire record. And this is why this function could be handy sometimes. Okay, so we remove this site from our list, and now we're creating a final list. This is the target list. We want to download the data. Okay. Now we want to download the data. This function allows you to download the data. First, you have to reduce the site in your Merflux. So make sure you replace this one with your user ID and replace this one with your email. For the demonstration, I already saved some of the information into my environmental variable here. Let's run this. And this function, you can see we put final list into the site ID. So that means we can download the every single site through just one function. You can see here, I print out the flux of the file location, this variable here, and this there are roughly, I think there are 10 files being downloaded and saved to your temporary drive, my temporary drive here. And this is the path to each of the file we store in this variable. This is handy because now you have all the file in your directory. The next thing we did is we want to retrieve reading this file. You want to know where this file gets stored, right? So we have 10 here. The next thing we did is just a tip. Sometimes the download could take time, so it depends on your internet speed. So if you run into trouble about this downloading function, maybe try somewhere else. Don't download through Wi-Fi, or maybe through you have a better internet coverage there. Okay. The next thing we did is we want to read in this base file. Okay. And this function allows you to do that. And for the demonstration, we only read the first one. So the US ARM, this file. And I want to parse the timestamp also. So it's easier to handle the data after this. And I plot this latent heap variable. Yeah, because this site has a very long record, so it might take a couple seconds to load the file and plot everything. Just a second. Almost there. Yeah, after we are reading the file, now next thing we did before we see a plot, we can come back later. We can parse and try to interpret the data. There are certain functions, yeah, now it show up. This have, I think it's almost 20 years of the data. So that's why it take a long time to plot this file. And this is a latent heap for almost 20 years of record. The next thing we did is we want to understand, so what's in there, right? First thing, this could be handy is, okay, just tell me the definition of each variable. And this function allows you to do that. Let's take a look what's in there. And this is the most updated variable list supported by Mathflux. Let's tell you the variable name, description, what is the unit, and a typical range of this variable here. And this could be handy to understand what's in the data. The next thing is also handy is, okay, I want to know about the variable height. For example, some of the variable, what is the height of the measurement, and also what type of the instrumentation is used to measure this variable. And this variable information functions could be handy. Okay, now we download this. We can take a look of this variable info, what's in there. As you can see, it's a very similar structure, right? So we have a site ID here. You have a variable name here, and to tell you about okay, what is the height, and also the starting day of this height. And this, for example, for this site, and I think the CO2 111 being moved. So that's why that's a starting day is slightly different. And also, what is the instrumentation model? This is measured by 7500A. And yeah, etc. So this file could be handy if you want to understand. So the height, maybe the depth of the variable, and also the instrumentation model type. The next thing we did is we want to have some metadata of this site, right? So very similar, we mentioned before, download BIF. This function allows you to do that. Again, you need an ID and the email to download it. The file size is much smaller, so take only a few seconds to download this file. And after we download the file, now we can try to reading. We know the location of the file. and we subset of the metadata, just the final list we have. Let's take a look of this one. So the file structure of this metadata is not so human readable, as you can see here. So that's why we create another function, just help you to extract the target variable group you have interest. For the demonstration, we only focus on the canopy high, this variable. Let's extract the target metadata. And we put this back to BIF-HC. Now this is more human readable, okay? Very similar structure. We have a site ID. What is the canopy high here? This is a mean canopy high and the date of the measurement. And sometimes there are additional comment about, okay, what type of vegetation or maybe how this canopy high being measured, etc. And because the metadata, there's the format of the metadata is by default is a character, and so some of the column you want to convert into, for example, like a timestamp. So that's why we converted timestamp into a time format, and also for another variable, this is canopy high, we convert it into a numerical variable. Then we can plot this canopy high. And this side they have maybe once or twice measurement. Canopy high measurement every year, so you can see very spotted, but pretty much over the entire record. The last thing is could be handy is if you're using the Merflux to write a paper, it could be handy about get a list of the contact of the site PI, the data you use, but also getting a DOI, data DOI of each of the data package you download. And this information could be handy when you're preparing your manuscript or publication. And let's take a look of this too. And you can, again, you use extract bed and this function to extract the information of the team member and also the DOI of this data set. And let's take a look of these two. Now this contact information for all the site we just used is available here. People's name, role, email, institution, and DOI give you an idea about the site. Each of the site, what is the DOI you should be citing for using the data. So this is the end of the demonstration. I hope you find this is interesting and can help you facilitate some of the research you'll be doing. And if you ever came across any problem, or maybe you'll find something could be handy in the future, just please feel free to contact me. I'll be happy to help you, or maybe we can work together to improve this package for future. And thanks again. I hope to see everyone next time.
Okay, so now this is the end of his presentation, because now he isn't available, so we will skip to the next one. Well,
yes, yeah.
Yeah,
so I guess for our next two live speakers, you can feel free to put questions in the chat kind of as we go, or I think, for the sake of time, we'll probably save questions for the end and kind of have time for discussion if that's available. But and at that time, you can feel free to raise your hand and ask your question live as well. But yes, our next speaker is Domenico Vitale. He is currently a researcher at the Euro-Mediterranean Center for Climate Change Foundation and collaborates with the ICOS ETC, which is the Integrated Carbon Observation System Ecosystem Thematic Center. He collaborates with that research infrastructure and testing and development of new methods for the processing of eddy covariance data. His main research interests include data mining, time series analysis, stochastic processes, quality control, uncertainty estimation, and missing data imputation. He's a developer and maintainer of the R package RFlux, which is an R graphical user interface for processing eddy covariance raw data. So Domenico, take it away. Thank you,
Thank you, Will. Can you see my screen? Thank you for the presentation.
Yes.
Okay, so I have prepared just some slides to show the main functionality of our Flux packages. So our Flux packages is designed to processing eddy covariance raw data, and it has been developed in the context of the IACS research infrastructure. And rFlux basically implements the data cleaning procedure described in the paper published some years ago in BioGeosciences journal. rFlux is freely available and can be downloaded from a GitHub repository, as you can see from this slide. So why rFlux? Why we implement rFlux? Why we develop rFlux? So the need is to clean dataset, clean alpha-hourly dataset without the need of researcher intervention. So the main need of rFlux is, or better, the eddy covariance researcher is to reduce or avoid, or at least reduce the presence of any source of systematic error affected eddy covariance raw data. But how to do that? So there are several ways, and by means of rFlux, it's possible to do that in a full automatic way. That is by means of a fully automatic data-driven procedure. Such a characteristics allow to reproduce the results any times, to reproduce the results in any time you want. The processing pipeline implemented in rFlux involve three main steps. Data preparation, which consists in convert raw data in a suitable format for rFlux, but also in this stage it's possible to apply the spiking procedure and a time lag detection procedure based on new procedure described in different papers. The last, those related to the one related to time lag is a paper under preparation. The next step is to estimate flux. This step is basically done by means of EddyPro software, which I think you know. And the last step is to clean datasets, so to perform the data cleaning procedure in alpha-hourly time series. So about data preparation, I just outlined the importance of the spiking and time lag detection, because the presence of spike and the correct time lag detection means avoid the presence of systematic error. In this figure, for example, you can see two subsequent alpha hours of vertical wind speed and carbon dioxide concentration, where one of the series of carbon dioxide concentration is affected by two spikes. So the presence of this spike affects dramatically the cross covariance function and then also the flux estimation. Reliable flux and unbiased flux can be achieved only when the spikes are correctly removed. In fact, in this case, the amount of flux you can see in the cross covariance function on the right side of the figures is comparable to the one estimated in the subsequent half hour. Also, the time lag detection procedure is an important step. The commonly used approach is to apply the covariance is based on the covariance maximization, which perform well when fluxes are of high magnitude. In case of fluxes are of small magnitude, there are some problems in time lag detection. For example, in this figure, you can see an ideal situation where we have a well-shaped cross covariance function, which allow to identify correctly the time lag between vertical wind speed and nitrous oxide time series. But when fluxes are of small magnitude, as in the case of middle and top and bottom panel, so the use of covariance maximization is not the best approach. In fact, in this case, the time lag detected by covariance maximization is not able to identify the correct time lag. The approach implemented in rFlux involved a pre-whitening procedure. The pre-whitening procedure consists essentially in remove the serial correlation affecting each time series, and then consider the cross-correlation function between time series. As you can see in the right panels of this figure, you can appreciate the correct time lag detected by means of this new procedure. As a result of this, so the effect of the time lag can be also it can be seen in this figure. For example, by looking at this flux as this flux is estimated during nighttime. So when the approach used is based on the covariance maximization, fluxes during this period, night period, in black lines, are negative. So this is incoherent with the ecophysiological processes. Instead, when the fluxes are estimated by pre-whitening procedure, the fluxes become positive, as expected during night, where all the ecosystem processes are active. Also, in this figure, you can also appreciate how the stability of the time lag identified with the pre-whitening procedure respect to those estimated with covariance maximization. So these are two new procedures implemented in rFlux. Once data are prepared, so converting raw data standard and eventually subject to the spike and time lag detected, the flux estimation can be performed in rFlux by two commands. The getMD command, which consists in build the input file required by EDIPRO software to run. Consider also that getMD command can also allow to specify some processing option, for example, the method for time lag or spiking method, or the method used to the trend time series, as also the method used for tilt correction. Once created the metadata file, the point EDIPRO file, dynamic metadata file, etc. So all the files required by EDIPRO software, it is possible to estimate uncovered flux by simply run EDIPRO software, and this is done inside the rFlux library with the EDIPRO run command. Note also that EDIPRO should be installed on your personal computer, so it is not part of the rFlux, but need to be installed on your personal computer. Once fluxes are estimated, so we can start the last step, the most important step of the data cleaning procedure. So the rationale behind the data cleaning procedure is based on the fact that we have to flag fluxes according to three flags. No air flag, which means that fluxes are not affected by systematic error. So there are no evidence about the presence of systematic error. Moderate means that there are moderate evidences about the presence of systematic errors. And in this case, flux estimate could be biased, but the amount of this bias could be negligible. Severe flag when there are several evidences about the presence of systematic error. In this case, flux estimates are very likely to be biased. So in order to understand the rationale, the logic behind the data cleaning, I have built this figure where suppose that, where for each signal half hour, we don't know effectively which is the true flux value. But when we measure, we calculate the hourly flux, we know a version of the true flux value. In particular, the flux estimate can be considered as the sum of the true flux value plus a random error component. If we are able to perform n replication, n experiment, but this is not possible with the covariance system, with the covariance tower, So we have different version of the true flux value. If we average these different values, the different version, we can achieve the true flux value. So in this perspective, how we can distinguish between fluxes affected by systematic error or not? It is not simple. But ideally, fluxes affected by systematic errors move away from the true flux value. So the rationale behind is to find some procedure that allow us to identify flux estimate affected by strong evidences of systematic error between flux estimate affected by moderate evidences of systematic error. To do this, our flux implements a series of a sequence of quality control tests, and for each quality control test, we can define different two threshold values, and based on this threshold value, we can distinguish fluxes affected by severe error, or fluxes affected by moderate error, or fluxes unbiased, so that is not affected by any source of systematic error. Fluxes affected by severe error are directly discarded because we consider such fluxes strongly affected by systematic error. While fluxes affected by moderate error, so flux where the systematic error could be negligible, are examined in a two-step. In particular, fluxes affected by moderate error are discarded only if they result outliers, or better, only if compared to other flux value for the same time series results to be anomalous. The quality control tests implemented in airFlux are those described in the paper. Some of them refers to the fraction, refers to the presence of missing data, some other to the resolution problem, structural change problem. An important test is the kurtosis index applied on differential data. Also, stationary test in airFlux, we adopted we implement the test by MART, the integral turbulent characteristic test, and also other tests which are implemented more recently, which are based on time series characteristics, for example, the evaluation, the autocorrelation to leg one, and also tests related to the data distribution. In airFlux is implemented the instprob test function, which stands for instrumental problem test, which provide also a graphical output which can help the user to identify, to understand better the problem affecting some raw data. In this example, for example, you can see a series, an half-hour time series of vertical Wisp-Ind, which is affected by some problem. More likely there is some noise or some problem in unit conversion. More likely there is some problem, some noise which contaminated the time series. And this can be seen by looking at the autocorrelation function. So being a high frequency time series, we expect that the correlation between consecutive observation is close to one or close to one, because there are very similar observation. When the autocorrelation, so when the correlation to lag one is close to zero, of course there is some kind of problem. Note that a noise have an autocorrelation to lag one, only the noise have an autocorrelation at zero, at lag one near to close to zero. Another example is provided in this plot, where we have a structural change which affected, so a jump which affected the carbon dioxide concentration, and this is, as you can see, is evidenced by the key test, so the kurtosis applies on differential data, which is very high, and also by the test about the distribution. As you can see, in this case, we have a bimodal distribution, which is, of course, is responsible, so a situation like this is responsible to produce a lot of bias in the flux estimation, because we need to have a unimodal distribution when we calculate the fluctuation or in general the covariance between vertical wind and carbon dioxide. This is instead the graphical output of the clean flux function, which is the main function of the flux package. So here you can see the sequential procedure of the data cleaning, the sequential data cleaning procedure, where we apply the different kind of tests or quality control tests. As you can see, the original time series, which is plotted in the top panel, have 22% of missing data, and after the quality control test, of course, automatically implemented, automatically performed, reach about 50% of missing data after the stationary test, which is the main important test in data rejection, and about more than 50% after the removal of data identified as flagged as with a mother flag, identified as with a mother flag, and it resulted to be also outlier. But as you can see, the improvement in data quality is evident from this figure. Consider also that here we have more than 3 years of alpha-hourly data. Future implementation about Airflux will involve the extension to other greenhouse gases like methane, nitrous oxide. Also try to improve the flux estimation under non-stationary condition, because as I said before, the stationary test is one of the main important, have a strong impact on data cleaning procedure. Also implementing post-processing algorithm for gap filling, for example, for annual budget estimation with uncertainty, and so on and so on. So this is the main step. So I have finished my presentation. If I have some other minutes, I will show the code, an example of running code. So you can consider that there is a manual of a file package available on GitHub, where you can have all information about the function implemented in our Flux. There is also, there is also a vignette file where you can have a demonstration. You can run a demonstration of the Flux functionality. In this case, for example, you have an example of closed path raw data already imported in EDPRO, which can be used to perform analysis, to perform tests, quality control tests, and so on. Consider that this is the standard format required for our Flux. So the wind components and temperature, carbon dioxide and water vapor concentration, eventually diagnostic flag for sonic and gas analyzer, information about temperature, cell temperature, okay, in case you have a closed path system. This is an example of eddy covariance metadata table required by Airflux in order to build the input file for EDPRO. In this file, which can be uploaded as a CSV file, you can put information about all the variation occurring during the field campaign. So Canopy 8, so information about the site, information about the Canopy 8, information about the sonic anemometer position. Eventually in ICOS we have also to consider the invalid wind sector to exclude form during flux calculation, information about the gas analyzer, and then information about the file you have, the file format you have convert. This is an example of flux estimation. Flux estimation I have already shown in the slide. And then the data cleaning procedure. The data cleaning procedure is based on the following command, where you have to the command to calculate the quality control test statistic is the putcstat command. The input are the path where raw data are stored, information about the external timestamp. So if the timestamp refers to the beginning or the end of the time series, and eventually, if you want to save data or results in some path, with some specific file name. Once quality control test statistics are calculated, so the function which build the eddy covariance workset is the easy workset, which merge by building regular time series. So with missing value if there are, the easy work merge the output of EDPRO, the output of the quality control test statistics, the output of metadata file, the output of quality control statistics calculated
Monica, yeah,
yes.
Now that we are almost run a little bit late, can you just quickly just wrap up your presentation so we can move on to the next one?
Okay, I stop. If there are some question.
Yeah, I think we'll save questions for the end so we can go ahead and get to Jürgen's talk. But I love the graphical outputs that come along with those quality tests. That's really useful for the user. Yes, our last speaker will be Jürgen Nauer. He's a postdoctoral researcher at the Hawkesbury Institute for the Environment at Western Sydney University, where he works on modeling vegetation responses to climate change. He uses FluxNet data primarily to better understand how ecosystem physiology affects land atmosphere carbon and water fluxes. He is the developer and maintainer of the R package BigLeaf, which aims to derive functional ecosystem characteristics from meteorological and flux measurements. So you're going to take it away.
Yeah, thank you very much. Thanks for inviting me. So I'm Jürgen Knauer, and I'm happy to present the BigLeaf R package today. So what was my main motivation to design this package? So when we look at eddy covariance, what we usually look at is the measured fluxes, and that tells us very much like what is happening. But in many cases, we also want to know like, why is it happening? And this is where the BigLeaf R package comes into play. So it derives ecosystem functional properties that lets us better understand the underlying mechanisms that cause these fluxes, and lets us understand lead to a better process understanding and help us with the interpretation of the data. So to summarize it in one sentence, the package is all about deriving ecosystem functional properties from eddy covariance data and from the accompanying meteorological measurements. So just a quick overview of what the package does. Just a few functions that are included. So we can calculate or estimate surface roughness parameters, some physiological variables like canopy conductance, intrinsic water use efficiency, stomatal sensitivity to VPD. There are a few functions around the wind profile and the wind speed at certain heights above the canopy. Aerodynamic conductance is a big component, some formulations around the boundary layer conductance and the decoupling between canopy and atmosphere. Potential ET, surface temperature and surface VPD, light response curves, and energy balance closure, and then a bunch of meteorological variables that we need all the time, like something like the psychrometric constant, et cetera, et cetera. And last but not least, we can do some data filtering with the package, as well as unit conversions, which is something we need quite often, I'd say. And so all of this is based on the big leaf concept, which basically means that the ecosystem is reduced to one plane. So at this height here, the displacement height plus the roughness length, that's the big leaf. And the assumption is that all fluxes, or the sources and sinks of all fluxes, is located at this plane, which also means that we cannot really distinguish between canopy and non-canopy components. I will talk about this later a bit more. And so when do we apply this as R package? So we have, if you look at the processing pipeline, we have the raw data processing. That's pretty much what Dominique just presented. You see here a few example tools at the bottom. Then we would usually do the post-processing of the half-hourly data, something like flux partitioning. And finally, we can, what I called here, do some ancillary data processing. That's basically where Big Leaf comes in. And so Big Leaf does not interfere with the first two steps. So it basically assumes that your data have been correctly post-processed, and it then takes this as an input and calculates further properties, or from the fluxes. Just to quickly point you to this great list of packages and tools on the FluxNet webpage. So just a few technical things. So the package is under version control on Bitbucket. It's documented with R-Oxygen, which I can recommend. Of course, it's open source, and it's on CRAN for like 4 years already now. And so you can install it directly from CRAN, but this is maybe updated maybe once a year, plus minus. And so if you really want to have or work with the most updated version that includes latest bug fixes and so on, you can install it directly from Bitbucket with this command here. I'm just gonna demonstrate a few of the functionalities implemented. So the package comes with an example data set, which is basically a data frame of spruce forest in Germany. And so in this data frame, I think the way in many cases the data are structured are like, well, you have your data frame with your variables, like your meteorological variables, your fluxes, maybe some quality control variables. And what you can do first is filter your data. So for example, in this case, you apply the function. You have the first argument is the data frame. And then you say you want to quality control the data for the variables latent heat and sensible heat. And you specify that those variables that specify the quality have this extension here, QC. And you say that the good qualities are 0 and 1. And so this is filtered for quality, but then you can also filter along other variables, something like PPFT, for example. Well, let's say you're only interested in daytime data. So you would like to apply a minimum value of 200 micromoles, for example, but no maximum value. You don't want to filter high values. And so if you apply this function, it tells you like how many data got filtered out. So in this case, we excluded around half of the data set because, well, they are at night. So once you've done this, you can apply the functions. You can look at the manual as with any other function in any other R package. Usually how it works, you apply, supply the first, the data frame as the first argument. And then you just specify the name of the columns in that data frame as the main variables here, like wind speed, U star, and so on. And depending on the function, you can specify some more options, like what kind of model you apply and so on. This is how it works for like 80% of the functions, I would say. Pretty straightforward. So what I should mention is maybe that plots are not part of the package. That's basically up to the user. So it just calculates the quantity that you're interested in. But then how you plot this, whether you plot time series or functional relationships, that's basically up to the user. So that's not included. One feature I would like to mention is the flexibility of the inputs to the function. So as I said before, this is how you would usually work. But you could also replace, for example, the air temperature here with an external vector if you have that, or if you think that's better in this case. Or you could, for the last argument here, just replace it with a numeric value. In this case, then, like all the time series, it assumes to have this value, and it gets converted internally or adjusted internally in the function so that it works. Another useful thing is that you can just like apply supply vectors to the function. So in this case, this could be useful if you look at sensitivities of a certain variable, of a certain property to one of the input variables, such as VPD. So in this case, we test how sensitive it is, the surface conductance to changes in VPD, for example. We also have default variables, so function calls can be really, really short. But of course, you don't have to use default names. Just to show you a few example applications. So the thing that's most common to calculate, I would say, with the package are like ecosystem functional traits. For example, the intrinsic water use efficiency or the related G1 parameter, which you can derive once you have the surface conductance. So in this study, for example, they looked at this property for two sites. One is a corn field, one is a wheat field. And what was nice to see here is, first of all, that it's really constant over the years, or except for a few outliers maybe, for both sides, but also that corn shows a high water use efficiency, so a lower G1 compared to the wheat side, which is also what we see with leaf physiological data. In this paper, a whole ecosystem was fertilized with nitrogen and phosphorus. And in this case, they looked at the G1 parameter again, so water use efficiency basically, and how that changes with nutrient addition. And they could detect changes in water use efficiency with this treatment. So something that you would probably not immediately see with the fluxes. Another nice concept is the stomatal sensitivity to VPD, which has been around in the literature for quite some time. This is also implemented in the function, and this can be also applied to different ecosystems. So in this case, two ecosystems were compared under different conditions. So how does surface conductance change with VPD under high and low soil water conditions? So it's good to compare, to do comparison across sites for these functional properties. And you could also do it further and basically calculate it for the whole of FluxNet, basically, as was done in this paper, where ecosystem functioning was characterized like across the network, and some of the functional properties implemented in the network were included in this study. Just a few cautionary remarks, I would say. So these functional properties that the package lets you calculate, they all depend on the input. So that's usually the carbon and water fluxes like latent heat flux and NEE. And we all know it's very challenging to calculate them and to process them. And they all have, they have some uncertainty, some errors, and they tend to propagate through, right? So, so we have a bit of a trade-off here. On the one hand, the interpretation of our variables or functional properties increase as we go down the calculations. But on the other hand, the uncertainties also propagate and tend to decrease, tend to increase as well. That's something to keep in mind and to be careful when applying these functions. I don't think there's a silver bullet on how to characterize the uncertainty, but in some cases it makes sense to, for example, for GBP to just apply different partitioning methods and look at the ensembles of like how the values differ and how that translates into the functional properties. Just shortly, pros and cons of the big leaf approach. You could argue that on both sides, you could say pro and con is it's simple. And so what that means for the pros, it's like you don't need any assumptions. So you could argue that also your eddy covariance data see a big leaf as well. So in the traditional application, the data itself, you can't distinguish between soil and canopy components, for example. An advantage is you don't usually need a lot of ancillary data, right? So you can just use the fluxes, and in most cases, that's sufficient. And this also makes it suitable for multi-site comparisons, so even across the whole FluxNet, or if little is known about a site. That doesn't, of course, mean if you know your site very well that you shouldn't apply this package. Can, of course, always do that. And cons, as I mentioned before, it can just give you about ecosystem characteristics. So it does not vertically or horizontally resolve the fluxes in any way. And as such, it's also not able to distinguish soil from vegetation fluxes, which is something you have to keep in mind when you work with your sites. So one last thing. So I see Big Leaf also as a community effort. And so there are different ways you could contribute, and I encourage you to do that. So there's, first of all, report bugs. So I'm sure there's still bugs in there. And you can tell me directly, or you can do that via the issues tab on the Bitbucket page. Or you could also contribute functions, or functionality, or ideas or suggestions. So either I could implement it directly, or you could implement it yourself. For example, branch off on Bitbucket and do push request. So there's several ways on how to do it. And I think the only criteria that it should be published, or it's about to be published, and it's within the scope of the package. And just one example of how that worked really well recently. So a PhD student came up with a function of how to characterize temperature optima of GPP across sites. You see an example here. And she had an R code that we thought would be really nice to integrate into the package. So we branched off. She worked on it separately, and then she merged back in, and it's now included in the package. And I guess the advantage is for you that you also get a bit more visibility probably. So the package has around 150 or 200 downloads a week. So your paper would also be mentioned in the documentation. So I think it's a good idea to contribute if that makes sense. And that's all from my side. You can find more about the package here on this webpage, on the CRAN webpage. I'd like to thank my co-authors here, contributors to the package. And yeah, you find everything else here. That's all from me. Thanks.
That's a lot for your fabulous presentation on the two packages. Now we are just a little bit behind our schedule, but if we have some quick question for those two packages, we can hold on just a few minutes to ask the author to answer those questions. Do the audience have some very quick questions?
While people are starting to ask their questions, I know that some people probably have to leave. So I'll go ahead and just make a few announcements really quickly, kind of on the FluxNet ECN side of things. And thank you very much to the speakers, as well as for our audience members for being here today and contributing your time and attention. as well as the Ameriflux Management Project, who helps us with a lot of these logistics. Let's see, we're anticipating to host a webinar in July that's going to feature work from the regional networks across Asia, and we'll notify the network about that through the listserv. And you can join the listserv and learn more about ECN through this link that I'm going to pop into the chat. So yeah, with that, do we have any questions for people who can stick around?
If not, maybe I have a very brief question. So for the rFlux, it is related to the AdiPro, or it's totally independent of AdiPro? Domenica, yeah, just this simple question for you.
So it depends. So if you have process your data by means of AdiPro, you can use rFlux to clean dataset. So depends. So each step is independent from the other. Okay. So as I said in the presentation, AdiPro is not part of rFlux, but is used by rFlux during flux estimation. So we prefer to use a well-known, well-established software during flux estimation because it is a major project, AdiPro, so there is no need to implement other software for flux estimation. This is the mean we do not implement any function for flux estimation.
Okay, cool. And do we have any question for Big Leaf package? Yeah,
I have one. If it's nice that you don't need a ton of ancillary data sources to really use that package, but I was wondering if maybe someone at a site was going to focus on measuring a few extra ancillary variables, like maybe what are the most important ones to use in the package. I'm also curious about maybe, has anyone tried to use this package with like a SAPFlux data? Because I feel like that would be an interesting application as well.
Yeah, so regarding the ancillary data, so you don't need them, but it's of course always good to have more data on your site and more knowledge. So LAI is something that comes to my mind first. Something like leaf size would be good for aerodynamic conductance. So, and everything else like soil moisture or phenology that really help. That's really not required, but it helps you to interpret the data in better context, and tells you more and more the more data you have. So whether that's leaf phenology, isotopes, soil moisture, yeah. And what was the second question? Sorry.
I was wondering about SAPFlux data. So
oh yeah, I think it could be applied in a very similar way, but I'm not aware of anyone who does that at the moment. But I think it can be done. Yeah.
Okay, cool. Now I think it's the end of our seminar, and we are very appreciated for your time, and we are run a little bit late. I'm sorry for that, and thank you very much for your understanding. And Gabriela, do you want to say something?
Hi, I just wanted to draw attention. We just had one last question get dropped in the chat. You want to read that?
Okay.
Thank you.
Does Big Leaf also work with vegetation indices like NDVI or green index?
Yeah, so it doesn't not require them as input variables. I would consider them as ancillary measurements that help you interpreting the data, just like any other measurements you have at your site, like phenology or yeah, any other measurements. So that just helps you to better interpret your data in the right context.
Okay, cool. Now I guess we have to say goodbye, everyone, and hopefully see you next time, next seminar in July. Goodbye, everyone. Thank you very much.
Thank you so much, everybody.
Thank you all.
Thanks.
Thank you, speakers. It was wonderful.